there is a number that ends the argument before it begins. Not a theory, not an interpretation, not a philosophical position that reasonable people can disagree about. A number, plain arithmetic. And once you hear it, the question is not whether something strange is happening inside quantum computers. The question becomes why nobody is saying this clearly enough for the weight of it to actually land. The number is this: 2 raised to the power of 300. Write it out and it has roughly 90 digits. It is approximately 2 times 10 to the 90th power. And the total number of atoms in the observable universe, every atom in every star, in every galaxy that has ever been detected, measured, photographed, or theorized about, is approximately 10 to the 80th power. A 300-qubit quantum computer simultaneously inhabits more computational states than there are atoms in everything we can see in any direction from any point in space to the absolute edge of the observable cosmos. And here is the part that breaks the comfortable explanations. We are already past 300 qubits. IBM's Condor processor, announced in 2023, has 1,121. Google's Willow chip, announced in December 2024, has 105 physical qubits, but demonstrates something that changes the arithmetic of what is coming entirely. And the roadmaps from every major player in this field point toward millions of qubits within this decade. The computation is not fitting inside this universe. It has not been fitting inside this universe for a while now, and the machines give correct answers every single time they run. That is the thing nobody says loudly enough. Not the speed, not the encryption threat, not the pharmaceutical applications or the material science breakthroughs or the artificial intelligence implications, all of which are real and all of which we are going to get into. The thing that changes the entire picture is that we have built a machine that demonstrably requires more computational resources than the observable universe contains, and the machine works, and nobody can fully explain where the work is happening. Not Google, not IBM, not the physicists who designed the architecture, not the engineers who cool these things to 20 millikelvin, colder than the vacuum of deep space, to keep them running. The machine works. That is not in dispute. The question of why it works, the real why, the one that requires you to point at a physical substrate and say, there, that is where the computation lives. That question is genuinely open. And the options that remain, once you follow the physics, honestly are not comfortable. Before we go further, I want to be direct about something. There is a lot of content about quantum computing right now that borrows the language of terrifying discoveries and reality-breaking breakthroughs, while actually saying very little. What I am going to do in the next hour is the opposite of that. Every claim in this script has a source. Every number is real. Every physicist mentioned is a real person whose actual published work I am drawing on. When I am in the territory of established physics, I will say so. When I am in the territory of interpretation and genuine scientific debate, I will say that too. The goal is not to scare you. The goal is to give you the actual picture clearly enough that you can form your own view of what it means. And the actual picture is strange enough that it does not need any embellishment. Let us start with what a qubit actually is, because the popular explanation you have probably heard is slightly wrong in a way that matters. A classical computer stores information in bits. A bit is a physical system that can be in one of two states. Call them 0 and 1. The transistor in your phone right now is either conducting or not conducting. Either it is letting electricity through, or it is blocking it. On or off. That is the whole game for classical computation. Billions of transistors, each one a binary switch, toggling billions of times per second. A qubit is different. A qubit is a quantum system that can be in a superposition of 0 and 1 simultaneously. And this is where the popular explanation usually says something like, it is both 0 and 1 at the same time, which is technically accurate but slightly misleading in a way that loses the most important part. A qubit in superposition is not like a coin that is secretly either heads or tails and you just have not looked yet. It is not like a door that is in an intermediate position between open and closed. The classical analogues all fail for the same reason. They all involve a system that is in one definite state that we just do not know. A coin in the air has a definite orientation. We just cannot see it yet. A quantum system in superposition does not have a definite state, not secretly, not in some hidden variable we have not found. The experiments that close that question, experiments that earned the Nobel Prize in Physics in 2022, are definitive on this point. There is no hidden variable. There is no deeper classical layer underneath. The superposition is the reality. What a qubit actually does is exist in a combination of both states described by something called a probability amplitude, a complex number that encodes not just the likelihood of each outcome, but also something called the phase. And the phase is everything. The phase determines how different superpositions interfere with each other, amplifying some paths, cancelling others. And quantum computation, at its core, is not about storing more information in a single bit. It is about using interference between probability amplitudes to make wrong answers destroy each other and let correct answers survive. That is the mechanism, not speed, not parallelism in the ordinary sense. Quantum algorithms are designed so that the computational paths leading to wrong answers cancel each other out through destructive interference, exactly the way two sound waves cancel when you invert one and play them simultaneously, and the paths leading to correct answers constructively reinforce. The machine does not search for the answer. It creates conditions under which everything that is not the answer ceases to exist. When you hear that a quantum computer can explore all possible solutions simultaneously, what you are actually hearing is a description of this interference process. The machine is structured so that the interference pattern it produces has only one surviving peak, the correct result. Now here is where the resource accounting becomes unavoidable. 10 qubits in superposition simultaneously represent all 1024 possible 10-bit combinations. Not sequentially, simultaneously, all at once. 20 qubits represent over 1 million. 50 qubits represent over 1 quadrillion. The number of simultaneous states scales as 2 to the power of the number of qubits, and that is an exponential function. It does not grow quickly. It does not grow very quickly. It grows in a way that has no adequate English word. A few dozen doublings, and you have exceeded any finite quantity you can physically point to. 53 qubits, the number in Google's Sycamore processor when it demonstrated quantum supremacy in 2019, simultaneously inhabits 9 quadrillion states. That is, a 9 followed by 15 zeros. More simultaneous computational paths than the number of cells in every human body on Earth combined. 300 qubits exceeds the atom count of the observable universe. 1,121 qubits, which IBM's Condor chip already has, inhabits a number of simultaneous states, so large that if you wrote it out in standard notation, the number would be longer than this entire script. And the computation is demonstrably happening. The interference is demonstrably occurring. The correct answers demonstrably emerge. Something is doing the work. Something is hosting the information. Something is the physical substrate of all those simultaneous states. Where is it? This is not a new question. A physicist at Oxford named David Deutsch asked it in 1985, before quantum computers existed as anything other than theoretical objects. He was working on a deeper question than most of his colleagues at the time, and his question was genuinely radical. Is there a physical machine that could, in principle, simulate any physical process, not model it, not approximate it, simulate it exactly, using the actual laws of physics as the operating system? And his answer, derived rigorously from quantum mechanics, was that a classical computer cannot do this, not because it is too slow, not because we have not built a big enough one, because a classical computer operates inside a single physical reality, and the computational resources required to simulate even moderately sized quantum systems exceed the physical capacity of any single physical reality. The state space of quantum mechanics, what mathematicians call Hilbert space, is genuinely larger than physical space, not as a metaphor, not as a convenient way of saying it is complicated. As a mathematical fact, the space required to fully describe a quantum system of moderate size exceeds the dimensionality of any physical space we have ever observed or measured. Deutsch's conclusion was stated plainly in that 1985 paper. If the computation requires resources that do not exist within a single instance of physical reality, the resources must exist elsewhere. And the elsewhere that is physically coherent with the mathematics of quantum mechanics is the many worlds framework. Parallel branches of reality, each running a piece of the computation, with the interference between branches, producing the result we observe. Most of his colleagues at the time either ignored the paper or treated it as interesting but unprovable. The community had been shaped by decades of influence from Niels Bohr and the Copenhagen interpretation, which held that quantum mechanics is a tool for predicting measurement outcomes, and that asking what is actually happening between measurements is a meaningless question. Bohr's intellectual dominance over the mid-20th century physics community was enormous, and his methodological preference for not asking about underlying reality had become something close to doctrine. But Deutsch was not asking a philosophical question. He was asking a physics question. Where does the computation happen? It is a question with a physical answer. And the answer the mathematics points to is not comfortable. To understand why the many worlds framework is the answer Deutsch arrived at, and why it is taken seriously by a significant portion of the physics community today, rather than dismissed as science fiction, you need to understand the problem it was designed to solve. Because it was not invented to explain quantum computers. It predates quantum computers by decades. It was invented by a graduate student at Princeton in 1957 who was trying to solve what is called the measurement problem, and it is one of the deepest unresolved issues in the foundations of physics. Here is the measurement problem stated as clearly as I can manage. Quantum mechanics, in its standard formulation, says that quantum systems evolve according to Schrödinger's equation. The equation is deterministic, continuous, and describes a system that stays in superposition. 2 outcomes remain in superposition. 10 outcomes remain in superposition. The equation never picks one. It just keeps branching, keeps evolving, all branches remaining real simultaneously in the mathematics. But when we measure a quantum system, we see one outcome, not a superposition, one definite result. The cat is either alive or dead, not both. The electron hits the detector at one specific location, not all locations simultaneously. Something resolves the superposition into a single outcome. And that process, called wave function collapse, is not described by Schrödinger's equation. It is a separate postulate added to the theory not because the mathematics requires it, but because the observations do. The measurement problem is this. Schrödinger's equation says the superposition continues, but measurements always give single outcomes. Something is wrong or something is missing in the standard picture, and no one has agreed on what. Hugh Everett III was a graduate student working on this problem for his doctoral dissertation. His supervisor was John Wheeler, who is important to this story in his own right, and who we will come back to. Everett's proposed resolution was, in retrospect, the most radical, simple thing anyone has ever written in a physics thesis. What if the equation is right, and there is no collapse? What if every possible outcome actually happens? Not probabilistically, in the sense that one wins and the others are discarded, but simultaneously, in separate branches of a universal wave function that never collapses. The measuring device entangles with the quantum system. The physicist reading the result entangles with the measuring device. The laboratory, the planet, the galaxy all branch into separate versions. One for each possible outcome. Each version real, each unaware of the others, because the branching process, decoherence, makes the branches transparent to each other. They no longer interact. They separate into distinct streams of reality. Everett was not claiming this was nice or convenient. He was claiming it was what the mathematics says if you take the equation seriously without adding collapse as an extra ingredient. Bohr dismissed it. The community followed Bohr. Everett's dissertation was cut down, made less ambitious, and published in a journal where it attracted almost no attention. He left academic physics almost immediately after receiving his degree. He went to work for the Pentagon doing mathematical modeling for nuclear strategy during the Cold War. He calculated mortality projections from radioactive fallout. He worked on weapons delivery systems. He drank heavily. He was, by most accounts, deeply unhappy. He died of a heart attack in 1982 at the age of 51, never knowing his framework would eventually become one of the most seriously discussed interpretations in physics. His ashes were thrown in the trash, his own request, because in the many worlds interpretation, no particular physical configuration matters. There is another branch where he is still alive. His daughter Elizabeth died by suicide in 1996. A note found with her said she was going to join her father in another universe. David Deutsch built a machine that runs on the framework both of them lived and died with. And the machine works. Now, I want to be careful here, because this is where popular accounts of quantum computing often go too far in one direction or not far enough in the other. The many worlds interpretation is not the only interpretation of quantum mechanics. The Copenhagen interpretation, in which quantum mechanics is a tool for predicting outcomes without asking what is really happening, remains widely used by working physicists. The pilot wave interpretation of de Broglie and Bohm proposes a hidden layer of classical determinism underneath the quantum behavior. The relational interpretation treats quantum states as descriptions of relationships between systems rather than properties of systems in isolation. There are others. No experiment currently distinguishes between these interpretations at the level of raw measurement outcomes because they all predict the same outcomes. The disagreement is about what the mathematics means, not about what the experiments show. But here is where the quantum computing question presses on the debate in a way that the philosophical discussions alone cannot. In every other context, you can choose your interpretation based on taste and proceed with your calculations. The Copenhagen physicist and the many worlds physicist make identical numerical predictions for every experiment. The interpretations are empirically equivalent. except that when you ask where is the quantum computation happening, the interpretations are not equal. The Copenhagen interpretation does not have an answer. It says the question is not meaningful. The computational states exist in the mathematics, and the answer emerges when you measure. Where the computation lives between the input and the output is not a question the Copenhagen framework addresses. Deutsch's argument is that this evasion is not sustainable. A computation requires physical resources. A machine that uses more resources than the observable universe contains is drawing those resources from somewhere. And where they come from is a physical question that demands a physical answer regardless of philosophical preference about whether to ask it. This is not settled. I want to be clear about that. There are brilliant physicists who disagree with Deutsch's framing, but the disagreement is no longer confined to philosophy seminars. Because the experiments that were honored with the 2022 Nobel Prize in Physics have closed one of the most important escape routes from the question. Let me explain what those experiments actually showed. In 1964, an Irish physicist named John Bell published a paper that transformed what had been a philosophical dispute into a testable physics question. Albert Einstein had been arguing since 1935 that quantum mechanics was incomplete. The apparent non-locality of entanglement, the fact that measuring one particle of an entangled pair seemed to instantly determine the state of the other, regardless of the distance between them, struck Einstein as unacceptable. He believed there must be hidden variables, some deeper layer of physical reality, some information carried locally by the particles themselves that determined their measurement outcomes in advance. The entanglement would then be nothing more than correlations built in at the beginning, like two gloves in separate packages, where opening one tells you about the other, because they were matched before being shipped, not because there is any connection between them. Bell showed that this intuition makes a testable mathematical prediction. If particles carry local hidden variables that determine their measurement outcomes, then the correlations between measurements on two distant entangled particles must obey certain numerical limits. These are Bell's inequalities, and quantum mechanics predicts those limits will be violated. The two theories give different numbers. The question is which numbers nature produces. The experiments that tested this question, beginning with Clauser and Friedman in 1972, continued by Alain Aspect in the early 1980s, and culminating in loophole-free tests by multiple teams in 2015, all produced the same result. Bell's inequalities are violated, not by a small amount, by large margins, with extraordinary statistical significance. Nature produces the quantum mechanical numbers, not the hidden variable numbers. Local hidden variable theories are ruled out, not disfavored, not in tension with some data. Ruled out by direct experimental test, confirmed across multiple independent laboratories using different techniques, and honored with physics' highest award. What this means is that there is no classical layer underneath the quantum behavior. There is no deeper deterministic reality where particles carry predetermined outcomes. The universe at its most fundamental level does not work that way. The correlations between entangled particles are real, non-local, and not mediated by any classical mechanism. And this is the point that connects back to quantum computing. If the correlations are real and non-local, if the relationship between two entangled particles is maintained without any classical signal passing between them, then the question of where quantum information lives takes on a different character. The information is not local. It is not stored in a particle, the way a classical bit is stored in a transistor. It is in the relationship between systems, and that relationship does not have a single location in space. In 2017, a Chinese satellite named Misius, named after an ancient Chinese philosopher who performed some of the first recorded experiments in optics, demonstrated something that should have received much more attention than it did. The satellite generated pairs of entangled photons and sent one from each pair to each of 2 ground stations on the surface of the Earth, separated by over 1,200 kilometers. The entanglement survived. The correlations between measurements at the 2 stations violated Bell's inequalities by more than 11 standard deviations. 1,200 kilometers of atmosphere, weather, the curvature of the Earth, relativistic effects from the satellite's orbital velocity. None of it broke the entanglement. The following year, Micius was used to conduct quantum key distribution between Beijing and Vienna, separated by over 7,000 kilometers. The first intercontinental quantum-secured communication. The entanglement held at planetary scales. Entanglement is not a laboratory curiosity. It is a global phenomenon. The resource that quantum computers exploit is not confined to the physical volume of the hardware. The correlations operate at scales that have no classical analog, maintained by no classical signal, explained by no classical mechanism. And the machines that exploit this resource are growing rapidly. Let me give you the actual timeline because it matters for understanding where this is heading and how quickly. In October 2019, Google's Sycamore processor, with 53 qubits, completed a calculation in 200 seconds. The best classical estimate at the time was that the same calculation would take the most powerful classical supercomputer approximately 10,000 years. IBM contested this estimate, arguing that with optimized algorithms and enough storage, their Summit supercomputer could do it in roughly 2.5 days. Google acknowledged the revision. Both sides agreed the fundamental difference in kind was real. A quantum machine had done something a classical machine could not practically replicate, and the debate was about the size of the gap, not its existence. In December 2024, Google announced Willow, and Willow did something that the entire quantum computing field had been pursuing as a theoretical target for 30 years. Something that changes the engineering picture in a way that is difficult to overstate. Willow demonstrated scalable quantum error correction below the fault tolerance threshold. To understand why this matters, you need to understand the central problem that has made large-scale quantum computing so difficult. Quantum states are extraordinarily fragile. A single stray photon, a vibration from a passing vehicle outside the building, electromagnetic noise from a power cable nearby, any of these can cause what is called decoherence, the collapse of the quantum state into a classical one. The computation is destroyed. The answer is lost. This is why quantum computers are cooled to 20 millikelvin, roughly 20 thousandths of a degree above absolute zero, colder than the cosmic microwave background radiation, which is the ambient thermal glow filling the entire universe in every direction left over from the Big Bang. These machines are cooled to temperatures colder than the average temperature of outer space, and the entire engineering challenge of quantum computing reduces to a single sentence: keep the computation hidden from the universe long enough to get an answer. Because the moment the environment interacts with the qubits, the moment any particle from the outside world entangles with the quantum system and carries away even one bit of information about the state, the superposition collapses. The computation ends. The quantum advantage disappears. Error correction is the engineering response to this problem. Rather than trying to prevent all errors, you encode the logical information redundantly across multiple physical qubits in a pattern that allows errors to be detected and corrected without measuring the logical state directly. You measure certain relationships between qubits, not the qubits themselves. The relationships tell you whether an error occurred without revealing the quantum information being protected. The error gets corrected. The computation continues. The threshold theorem, proven theoretically in the late 1990s, says that if the error rate of individual physical qubit operations falls below a certain critical value, roughly around 1% for many architectures, then error correction can reduce the logical error rate arbitrarily. Below the threshold, more physical qubits means lower logical error rates. Above the threshold, more physical qubits means more total errors. What Willow demonstrated is that real hardware can operate below this threshold and that the theoretical prediction holds in practice. As they increased the number of physical qubits encoding each logical qubit, the error rate dropped, and it dropped in the exponential way the theory predicted. The machine gets more stable as it gets bigger. More components means lower error rates. This is the opposite of every engineering intuition built up from centuries of working with complex classical systems, where more components always means more failure modes. Willow breaks that rule, and this is where the philosophical and the engineering intersect in a way that is difficult to dismiss. The error correction works by encoding the logical qubits information in a non-local way across many physical qubits. The information is not in any one physical qubit. It is in the pattern of relationships between them, and this non-local encoding makes the information structurally inaccessible to local environmental disturbances. Random noise hits individual qubits locally. The logical information lives globally. The noise and the information are not speaking the same language, so to speak. The noise cannot corrupt what it cannot access. This is the same structural principle as topological protection, which is the approach Microsoft has been pursuing for over 2 decades with a different type of qubit entirely. Microsoft's bet is on something called Majorana zero modes, named after the Italian physicist Ettore Majorana, who in 1938 proposed a class of particles that are their own antiparticles. Majorana published his theory in 1937. Then, in March of 1938, he boarded a boat from Palermo to Naples, was seen by other passengers during the voyage, and was never seen again. No body was ever found. He was 31. The mystery of his disappearance has never been definitively solved. His physics survived him. Majorana zero modes are not the particles he originally described, but quasi-particles that emerge in certain condensed matter systems, particularly topological superconductors. What makes them relevant to quantum computing is this: a Majorana zero mode cannot exist alone. It always comes in pairs, and the quantum information is not stored in either mode individually. It is stored in the correlation between the two modes, which can be physically separated from each other. If the information is not located in any single place, then local disturbances cannot destroy it. To corrupt the logical qubit, you would have to simultaneously disturb both modes in a correlated way. Random thermal fluctuations essentially never do this. The protection is not external, as not a refrigerator keeping the system cold or a shield blocking electromagnetic interference. The protection is intrinsic to what the qubit is. The information has no location. The environment is effectively blind to it. In February 2025, Microsoft announced a chip called Majorana 1, which they described as the first demonstration of topological qubits reliable enough to serve as a computing platform. The physics community received this with measured enthusiasm and appropriate skepticism, both justified. Microsoft has been working toward this for more than 20 years and has had previous claims in this area scrutinized carefully, including a 2018 paper that was ultimately retracted after errors in data analysis were identified. The 2025 announcement was more carefully documented and cleared initial peer review. Independent verification was still ongoing at the time this was written. The honest answer is that if it holds up, the engineering timeline for practically useful, fault-tolerant quantum computing shortens dramatically, potentially by a decade or more. But here is the thing that I find most interesting about topological qubits, and it connects back to everything we have been building toward. In every classical system, information has a location. A bit is stored in a transistor that is in a specific place. A classical hard drive stores information in magnetic domains at specific positions. Information is tied to physical objects in physical locations, and we barely notice we are assuming this because it is so fundamental to how classical systems work. Topological qubits store information in the relationship between places. The information is real. You can read it, compute with it, transmit it, but you cannot point to where it is. There is nowhere for it to be.